Okay, biochemistry, welcome to part 1 of thermodynamics, where we're going to talk about thermodynamic laws and concepts. So after watching this, you should be able to relate G, S, H, and T. What are they? How do they relate to each other? What's the equation? You should be able to explain the first law of thermodynamics and the second, and compare reversible, irreversible, and equilibrium. What does that mean? Okay, so first off, this should be a pretty easy review from your general chemistry. Delta G equals delta H minus T delta S. This is how all of these letters relate. So here, the delta G, this is the free energy. So what free energy means is that this is the energy that's available to do work. And we want, for a spontaneous process, delta G is less than 0. For non-spontaneous, delta G is greater than 0. It's a positive number. And at equilibrium, delta G equals 0. So keep that in mind. Positive number, non-spontaneous. Negative number is spontaneous. Equilibrium and equals 0. Okay. Next up, delta H. This is the enthalpy. This is the heat of the reaction. And if you remember back to reaction coordinate diagrams, where you have a reaction occurring, and we've got the reactants and the products and the energy, which increases this way, and the reaction coordinate, which increases this way. The delta H is this distance. It's the distance between the products and the reactants. So in this way, delta H is a state function, because it doesn't matter how you got there, and this could actually look like this or like this. It doesn't matter. So all that matters is the starting point and the ending point, and you've got your delta H. So in this instance, this delta H is less than 0. It's giving off energy. This is exothermic. If it were to gain energy, then the products would be higher than the reactants, and that would be endothermic. Delta H greater than 0 was endothermic. It brings in energy, like ice melting. Okay. Next up, T. This is the temperature, and it's pretty safe to assume that it's in Kelvin, but working through these thermodynamic problems, don't always make that assumption. Always check to see if the other units are Kelvin or Celsius. This is going to be very, very important. In this equation, it's typically Kelvin. So we know that this value is always going to be positive, because there's no such thing as a negative Kelvin. Okay, and then the final piece of this puzzle is S, and that is the entropy. This is the randomness or the disorder. So we like an entropy that is increasing in disorder. So we like a delta S to be greater than 0. This means more disorder. When delta S is less than 0, that means it's more ordered, which doesn't really make sense if you consider cleaning up your room. So if you don't clean up your room, that doesn't take a lot of energy, and it will naturally fall into a state of chaos, because the second law of thermodynamics states that the entropy of the universe is increasing. And we'll talk more about that in a second. Okay, so these are the important players in this game. Delta G, delta H, T, delta S. And we're going to talk more about that in the next lecture. So just remember this. None of this should be new to you, but it's totally okay if it is. Okay, so we already talked about the second law of thermodynamics, so let's review the first law. First law of thermodynamics is called the conservation of energy law. So, and it states that the energy in a closed system is neither created nor destroyed. So what this really means is that energy will transform like a transformer, like a robot in disguise, but it can't be made or destroyed. So it's really going to change from like kinetic to potential. Making and breaking of bonds is totally legit, but we're not going to create energy out of nothing. You can't get something for nothing. Okay, so a major theme in biochemistry is that we can couple energy releasing processes with energy absorbing processes to make them more favorable, and we see that through the use of ATP, the energy currency in the cell. If you remember the structure of ATP, it's got adenosine and 3 phosphates. Well, the hydrolysis of the last phosphate is extremely favorable. So we can couple this extremely favorable reaction to an extremely unfavorable reaction, and overall it can drive the process forward. So this is a huge theme throughout thermodynamics and biochemistry. And then the second law of thermodynamics that I mentioned earlier is that the entropy of a system increases. So that would mean the change in entropy is going to be greater than 0. You're not going to see a situation where you go and you mess up your room and you walk back and it's magically cleaned. Unless there's someone else putting in some outside effort on your part, that's simply not going to happen. You can't take sugar and put it in a beaker of water and then expect the sugar molecules to be completely organized at the end of the day. That's not going to happen. But when we consider just a system, we're never really looking at just one cell or one reaction in a cell when we're thinking about biochemistry. So another way that we can consider this, that we've always found true, is instead of saying system, we can say the entropy of the universe. This is a much better word. And the universe is the system plus the surroundings. And this is going to be very important for how enzymes can bind a substrate. Because if you think about that, we're taking two things, so that situation is disordered, and we're creating one thing, so that's creating order, if we just look at the system. But when we include the surroundings, what we see is that the entropy of the entire universe actually is increasing, even though we're taking two big things and creating one thing. So this is going to be very important as we come up in proteins and enzymes and catalysis. And the last thing I want to talk about is reversible, irreversible, and equilibrium. So, reversible. These reactions are drawn like this. They're typically like A is becoming B, B is also becoming A. There's a forward, there's a reverse. These are typically near equilibrium. There are also irreversible reactions. So that would be like A becoming B, straight up. These are typically far from equilibrium, but these are trying to gain equilibrium. So these will eventually move toward equilibrium. So this is very different than spontaneous and non-spontaneous. Okay, and then the final thing I want to talk about is equilibrium, and here I'll show A going to B again. So we have these rates, how fast A is becoming B, and how fast B is becoming A. So at equilibrium, these rates, K1 equals K minus 1. The rates are the same. That has nothing to do with the concentration of A, the concentration of B. It has nothing to do with that. It's just that A is becoming B at the same rate that B is becoming A. nothing to do with concentration, so keep that in mind. Some of this vocab can be pretty intense and intimidating until you remember that you've already learned this in general chemistry.